So if we look at historically where we're coming from on this, so surface roughness measurement and characterization goes back to the 1930s. And one of the first things people did was calculate the average roughness. So we're dealing with a profile with a number of distinct height measurements. So for the SA, which would be over a surface, and the RA, which is over a profile, it's the arithmetic average. So, and we take the absolute value. So think for a minute why it might be important to take the absolute value. So we're dealing with displacement from a mean line. There's negative points and positive points. If I really have the right mean line, and I add these all up, keeping track of the sign, not taking the absolute value, they should add to 0. So I have to take the absolute value, otherwise this is a meaningless exercise. So that is the most used topographic characterization parameter, RA or SA. And the one thing to keep in mind, this comes to us from the 30s. Now we have to keep using this. I'm going to be showing you some more advanced ways of characterizing the surface. But to tie in with the past, it's important to continue to use RA or report RA or SA. The root mean square, also standard deviation. Because what I've done essentially by putting a mean line in here is I've subtracted the mean. So all I have to do is take the z values and square them, and then I've got the standard deviation. So this is the first statistical moment. This is the second. You can also do the third and fourth for skew and kurtosis. But the thing to keep in mind, a couple things, when I'm dealing with the average, is that one big mountain looks like 2 little mountains. And since I'm squaring it or taking the absolute value, it's like 2 little valleys. So we can imagine that these 3 surfaces would behave very differently in all kinds of situations. But let's see, I thought I had one more thing there, sorry. They would be, so you might want to keep your system muted. I heard somebody there. If there's something important, maybe you can monitor people putting up their hands.
I'm checking that. I'm checking that.
Okay. Yeah. So if you could stop me, and if you have, or if somebody else needs to stop me, turn on your mic, but you may want to keep it off. So in any event, we would have the same RA or SA or SQ or RQ for these 3 surfaces, but we could easily imagine that they're going to behave very differently. And what I'm pointing out here, something we may get back to, the sampling interval is what we call the distance between 2 height samples. So in surface metrology, we're using sample much different than we usually do in material science. Material science, we call a sample almost anything we put under a microscope. And often it is. It's inconvenient to bring the whole ship into the lab, so we take a sample of the hull and then bring that into the lab and polish it up and measure it. But so here we're using sample more in, well, in a different sense. Okay, so some other height parameters. So here's a cartoon profile, and we have a certain length on this. We have the mean line, and the RT is frequently used. That's the peak to valley distance. So it just takes the lowest valley and the highest peak. The RP is the maximum peak height. So this is going from the mean line up to the peak. And then RV is the valley depth. So the valley depth plus the peak height should give us the maximum peak to valley over some length that we're evaluating from a measurement. So there are some variations on this. You'll see RZ sometime, and this means that we break this profile up into several sampling lengths and then do the maximum peak to valley and take the average of those. And same thing for the peak height, although we call it RPM and then RVM. So, yeah, for aerial measurements, as I said, we'd have an S. Now, note, there is no spatial knowledge contained in any of these. It's strictly heights. So I could take all my height measurements and reorder them any way I wanted. And I would have all of the same values. So I could reorder them somehow so I have much sharper valleys or sharper peaks. And we could imagine the surface would be much more dangerous for fatigue or much more much better for cutting or wear or grinding if I had sharper peaks. But I couldn't tell the difference by using these parameters. So let's take a look at a very simple exercise you could do in Excel. And we'll just take a look at a sine wave, and we can calculate the different parameters for that. So the RQ comes out to be 1 over the square root of 2, which if you're good at math, you could predict. RT is very simple, peak to valley, and RA, you just take a whole bunch of these heights and sum them up. All right, so let's consider that, and now let's add to it, or let's consider another profile with a much smaller amplitude. Now, usually in surfaces, they do come out like this. So the largest wavelength is also the largest amplitude, especially over some interesting scale range. So we can see that this has a much smaller peak to valley, much smaller RA and RQ. Now, if we add these two together, and so I've carefully tried to do this, so I've got blue and red adding to purple, but that doesn't look very purpley, but that does. In any event, so this might be a surface where we've got a small wavelength superimposed on a larger one. And what happens to RA? Look at this. RA is exactly the same if I add the little wavelength on the big one or not. Now the little wavelength, so this could be, let's make a surface so it's glossy or matte. This could be the part that makes it matte. That could be what we're interested in. And RA isn't going to help us at all in distinguishing those two. So anyway, so there's a little example.